E-waste is a major global problem as the volume of discarded electronics continues to grow rapidly. These devices contain both valuable resources like metals and plastics, as well as hazardous materials like lead, mercury, and cadmium. Proper recycling and management of e-waste is crucial to protect the environment, human health, and the global economy. We need to find sustainable solutions to collect, process, and recycle e-waste responsibly. This slide provides an overview of the e-waste challenge and the importance of effective recycling and management strategies. The growing problem of electronic waste, or e-waste, is a major global issue we need to address. Each year, we generate around 50 million tons of e-waste worldwide. This includes discarded electronics like phones, computers, TVs, and other devices. Unfortunately, only a small fraction, around 10%, of this e-waste is properly recycled. The rest often ends up in landfills or is improperly disposed of. E-waste is actually growing at a faster rate than any other type of waste, with a 20% increase in recent years. This rapid growth in e-waste is a serious environmental and public health concern that we must tackle through better recycling, reuse, and responsible disposal practices. The image on this slide depicts a polluted river with discarded electronics, highlighting the environmental degradation caused by e-waste. E-waste contains hazardous substances that can contaminate soil and water, posing risks to ecosystems and human health. The extraction and processing of raw materials for electronics contribute to resource depletion, including valuable metals and minerals. The production, transportation, and disposal of electronics generate significant greenhouse gas emissions, exacerbating climate change. These environmental impacts of e-waste are serious issues that need to be addressed through responsible waste management and sustainable electronics design. The image on this slide depicts the hazardous nature of improper e-waste disposal, with a person in a gas mask and gloves sorting through a pile of e-waste surrounded by hazardous symbols. E-waste contains a variety of toxic substances that can pose serious health risks if not handled and disposed of properly. Let's discuss 4 key health risks associated with improper e-waste disposal. Lead poisoning from batteries and monitors, which can cause brain damage and developmental problems. Mercury exposure from fluorescent bulbs and other components, which can harm the nervous system, kidneys, and developing fetus. Respiratory problems caused by the release of toxic fumes when e-waste is burned or improperly handled. Skin and eye irritations from exposure to chemicals like cadmium and beryllium, which can lead to more serious health issues with prolonged exposure. Proper recycling and disposal of e-waste is crucial to protect both the environment and public health. The life cycle of electronics is a complex process that involves several key stages. We'll start by looking at the first stage, raw material extraction. This involves mining resources like copper, gold, and rare earth elements that are used to make electronic components. Next, we move to manufacturing and assembly, where these raw materials are transformed into the electronic devices and components we use every day. After manufacturing, the devices enter the use and consumption phase, where consumers utilize them for various purposes in their daily lives. Eventually, these devices reach the end of their useful life and enter the disposal and end-of-life stage, becoming e-waste. The final stage is recycling and reuse, where valuable materials are recovered from the discarded devices and reused in new products. E-waste recycling is crucial for both environmental and economic reasons. Recycling e-waste reduces pollution from landfill leachate and harmful emissions from incineration. This helps protect the environment. Recovering valuable materials like gold, copper, and rare earth elements through recycling conserves natural resources and creates a circular economy. Recycling e-waste also generates revenue and creates jobs in the recycling industry. This provides economic benefits. The combination of environmental and economic advantages demonstrates the importance of proper e-waste recycling. The world map on this slide shows the global trends in e-waste generation over time, using different shades of red to indicate the growth. In the early 2000s, e-waste generation started to rise rapidly as electronic device adoption increased. By the mid-2000s, the global e-waste crisis gained more attention as volumes continued to escalate. During the 2010s, e-waste became the fastest-growing waste stream globally, surpassing other waste categories. Today, e-waste generation continues to rise, posing significant environmental and health challenges around the world. The small icons scattered across the map represent different electronic devices like smartphones, computers, and televisions, highlighting the diverse sources of e-waste. The arrows point to specific regions experiencing rapid increases in e-waste, underscoring the global nature of this issue. Smartphones, computers, batteries, and televisions all contain valuable materials that can be recovered and reused. Smartphones have precious metals like gold, silver, and platinum, as well as copper, tin, and rare earth elements. Computers contain precious metals like gold, silver, and copper, along with rare earth elements in the hard drive and other components. Batteries have valuable metals like cobalt, lithium, and nickel, which are essential for energy storage. Televisions contain valuable materials like gold, silver, copper, and glass, as well as rare earth elements in the backlight. Recovering and recycling these materials is important to reduce waste and extract the full value from these products. Precious metals like gold, silver, platinum, and palladium are essential components in electronic devices. These metals have unique properties that make them valuable in electronics, like excellent conductivity, corrosion resistance, and thermal management. Recovering these metals from e-waste is important for the circular economy, as they can be reused instead of mined from the ground. Gold is used in connectors, chips, and circuitry due to its conductivity and corrosion resistance. Silver has high thermal conductivity, making it essential for heat dissipation in electronics. Platinum is used in specialized components like sensors and fuel cells due to its corrosion resistance and catalytic properties. Palladium is found in connectors, switches, and circuitry, especially in smartphones and laptops, thanks to its conductivity and corrosion resistance. E-waste, or electronic waste, contains a number of hazardous substances that can pose serious health and environmental risks. Let's take a closer look at some of the key hazardous substances found in e-waste. Lead is commonly found in batteries, monitors, and other components. Exposure to lead can cause brain damage, developmental problems, and other serious health issues. Mercury is present in fluorescent bulbs, switches, and other devices. It can harm the nervous system, kidneys, and developing fetus. Cadmium, used in batteries, screens, and other components, can cause kidney damage, lung problems, and bone disorders. Chromium, found in circuit boards, resistors, and other components, can cause skin irritation, respiratory problems, and digestive issues. Beryllium, used in computer chips and other electronic components, can cause lung damage, skin irritation, and other health problems. Proper handling and disposal of e-waste is crucial to mitigate the risks posed by these hazardous substances. E-waste, or electronic waste, contains a number of hazardous substances that can pose serious health and environmental risks. Let's take a closer look at some of the key hazardous substances found in e-waste. Lead is commonly found in batteries, monitors, and other components. Exposure to lead can cause brain damage, developmental problems, and other serious health issues. Mercury is present in fluorescent bulbs, switches, and other devices. It can harm the nervous system, kidneys, and developing fetus. Cadmium, used in batteries, screens, and other components, can cause kidney damage, lung problems, and bone disorders. Chromium, found in circuit boards, resistors, and other components, can cause skin irritation, respiratory problems, and digestive issues. Beryllium, used in computer chips and other electronic components, can cause lung damage, skin irritation, and other health problems. Proper handling and disposal of e-waste is crucial to mitigate the risks posed by these hazardous substances. E-waste, or discarded electronic devices, is a growing environmental challenge. We'll cover the key steps in the e-waste recycling process to address this issue. First, e-waste is collected from households, businesses, and other sources. Next, the e-waste is sorted by material type, plastics, metals, glass, etc. The devices are then carefully disassembled to separate the components like circuit boards, batteries, and screens. Valuable materials like gold, copper, and rare earth elements are extracted from these components. Finally, The recovered materials go through smelting and refining to produce pure, reusable resources. E-waste, or electronic waste, is a growing environmental challenge as technology continues to advance rapidly. Collection of e-waste is a crucial first step, with efforts to gather it from households, businesses, and retailers. These collection programs often use designated drop-off points or curbside pickup to make it convenient for people to dispose of their old electronics. Once collected, the e-waste must be carefully sorted by material type: plastics, metals, glass, batteries, etc. This sorting process is essential for efficient recycling and to prevent contamination during further processing. Proper sorting allows the different materials to be properly handled and recycled, maximizing the recovery and reuse of valuable components. This slide outlines the key steps in the disassembly and dismantling process for e-waste. First, skilled technicians use specialized hand tools to carefully separate the components of electronic devices, minimizing damage to valuable materials. Next, wires, cables, and other materials are cut and separated for proper processing. Finally, magnets are used to remove ferrous metals like steel and iron from the waste stream, allowing for more efficient sorting and recycling. The images on this slide visually demonstrate these disassembly techniques, showing the precision and care required to properly handle e-waste. Material recovery and separation is a critical step in e-waste recycling. It involves a few key techniques: mechanical separation, using screens, magnets, and other equipment to separate materials based on their physical properties. Chemical analysis, techniques like X-ray fluorescence to determine composition and identify valuable metals and hazardous substances. Hydrometallurgical processing, using water-based solutions and chemicals to extract valuable metals. Pyrometallurgical processing, using heat and chemicals to extract valuable metals, an important step in metal recovery. Smelting is the process of extracting metals from their ores by melting them down at high temperatures. This uses heat and chemicals to separate valuable metals from impurities. Refining is the process of further purifying the extracted metals to remove any remaining impurities. Refining involves additional processing to improve the quality and properties of the metals. E-waste recycling is an important process for recovering valuable materials and reducing environmental impact. There are two main technologies used in e-waste recycling: manual dismantling and mechanical shredding. Manual dismantling involves skilled workers using hand tools to carefully separate components and materials. This is a precise and delicate process, ideal for recovering high-value materials, but it is labor-intensive and requires specialized skills. Mechanical shredding uses large machines to break down e-waste into smaller pieces, separating materials based on their physical properties. This is an efficient way to process large volumes of e-waste and is suitable for separating metals and plastics. However, mechanical shredding can damage valuable components, so further processing may be required. Manual dismantling allows us to carefully separate valuable components from electronic waste. This helps minimize damage to recyclable materials, preserving their value. However, manual dismantling is labor-intensive and requires specialized skills and training. It can also be time-consuming, so may not be the best approach for large-scale operations. We'll need to weigh the advantages and disadvantages to determine the right approach for our needs. Mechanical shredding is an efficient way to process large volumes of e-waste, reducing the size of materials for easier handling and separation. It's an effective part of the recycling process, helping to separate metals and plastics. However, shredding can also damage valuable components, making them less suitable for recovery. Additionally, the shredding process can generate fine particles that pose health risks to workers and the environment. We need to carefully balance the benefits of mechanical shredding with the potential downsides and ensure proper safety measures are in place. Hydrometallurgical processing is an effective technique for extracting valuable metals like gold and copper. It's an environmentally friendly approach that minimizes air pollution and waste. However, it requires careful handling of chemicals to avoid contamination. The process can also be complex and requires specialized equipment. Pyrometallurgical processing is an effective method for extracting metals like copper and tin from e-waste. It can handle large volumes of e-waste efficiently, making it a scalable recycling solution. However, this process can generate air pollution that requires special emission controls. It's also an energy-intensive process that contributes to greenhouse gas emissions, which is an environmental concern. The advantages and disadvantages need to be carefully weighed when considering pyrometallurgical processing for e-waste recycling. The Basel Convention and Stockholm Convention are two key international agreements that regulate the movement and disposal of hazardous waste, including e-waste. The Basel Convention aims to prevent illegal dumping and promote environmentally sound management of e-waste. The Stockholm Convention targets persistent organic pollutants, POPs, found in e-waste, like polychlorinated biphenyls, PCBs, and brominated flame retardants, BFRs. Many countries have also implemented their own national and regional laws to address e-waste management, such as the EU's e-waste directive. These regional regulations are essential for tackling e-waste challenges at a local level in different parts of the world. The Basel Convention is an important international treaty that aims to regulate the global movement of hazardous waste, including e-waste. It prohibits the export of hazardous waste from developed countries to developing countries without their informed consent, helping prevent illegal dumping. The convention promotes environmentally sound management of e-waste through recycling, reuse, and proper disposal practices. It fosters international cooperation and coordination on e-waste management, facilitating information sharing and capacity building programs globally. This collaborative approach is crucial for addressing the growing challenge of e-waste, which has significant environmental and health impacts if not managed properly. The EU e-waste directive is a key policy aimed at improving the management and recycling of electronic waste across Europe. It sets collection targets for specific categories of electronic devices, ensuring that a minimum percentage of these products are collected for proper disposal and recycling. The directive also specifies recycling requirements, mandating minimum recycling rates for different types of electronic components to promote a more circular economy. A key aspect of the directive is the principle of extended producer responsibility, EPR, which holds manufacturers accountable for managing the end of life of their products. To enforce compliance, the directive empowers market surveillance authorities to monitor the market and impose sanctions on non-compliant producers and importers. The U.S. lacks a comprehensive national e-waste policy, with each state having its own laws and regulations, resulting in a patchwork of approaches. Some states, like California and Texas, have robust recycling programs, while others, like Montana and Wyoming, have limited or no e-waste regulations. The lack of a uniform national standard can create difficulties for businesses operating across state lines, but it also offers an opportunity to implement innovative e-waste management solutions at the state level. The map on this slide shows the varying levels of e-waste legislation across different U.S. states. Some states have strong e-waste policies, shown in bright green, while others lack robust regulations, indicated by the dark red areas. This slide outlines 4 key components of state-level e-waste legislation. Collection and recycling requirements. Many states mandate that manufacturers, retailers, or consumers collect and recycle certain electronic devices. Extended producer responsibility, EPR. Some states hold manufacturers accountable for the environmental impact of their products throughout the product lifecycle, including end-of-life management. Bans on landfilling. Several states prohibit the landfilling of specific types of e-waste, encouraging recycling and reuse. Fees and incentives. Some states use fees on electronic sales or financial rewards for recycling to encourage responsible e-waste management. The tilted and dynamic map conveys a sense of urgency around the need for comprehensive e-waste policies across the country. The image on this slide depicts a gloomy and polluted landfill filled with discarded electronics, highlighting the environmental impact of improper e-waste management. Limited infrastructure. Lack of dedicated recycling facilities and trained personnel can hinder proper e-waste management, leading to improper disposal. Lack of consumer awareness. Insufficient understanding of e-waste hazards and the importance of responsible disposal contributes to improper disposal. Illegal e-waste dumping. Criminal activities involving the illegal export and dumping of e-waste in developing countries pose significant environmental and health risks. Improper recycling techniques. Unsound recycling practices, including the use of harmful chemicals and inadequate separation of materials, can result in environmental pollution and health issues. Many regions lack dedicated e-waste recycling facilities, forcing people to dispose of electronics improperly or ship them long distances. This can lead to illegal dumping, pollution, and health risks. There is a shortage of trained professionals to handle the efficient and safe processing of hazardous e-waste. This results in improper disassembly, material recovery, and environmental damage. Addressing these infrastructure and skills gaps is crucial to responsibly managing the growing volume of electronic waste worldwide. Many consumers are unaware of the serious environmental and health risks associated with improper e-waste disposal. There is a lack of readily available information about e-waste recycling options and regulations in many communities, leading to confusion and a lack of action by consumers. Convenience often takes priority over environmental responsibility, as consumers may choose to simply discard old electronics in landfills rather than seeking out proper recycling channels. Raising awareness and providing clear, accessible information about e-waste recycling is crucial to address this growing problem. Illegal e-waste dumping is a major environmental issue, with waste being exported to countries with weaker regulations and often disguised as other types of waste. This waste is then dumped in open landfills without proper segregation or treatment, exposing the environment to toxic substances. Informal recycling practices are also common, where hazardous materials are extracted and handled unsafely, leading to health risks. The leakage of these hazardous materials into soil and water bodies contaminates ecosystems and poses serious risks to human health. This slide highlights the various stages of this illegal e-waste trade and the devastating environmental and health consequences. E-waste recycling is a critical issue, but improper techniques can have serious environmental and health consequences. Incineration of e-waste releases toxic fumes that pollute the air and put people's health at risk. Using strong acids to extract valuable metals from e-waste can contaminate water sources and damage the environment. Directly burning e-waste through open burning also releases hazardous substances into the environment. Mixing different types of e-waste together can contaminate valuable materials, making recycling more difficult and less effective. We need to ensure e-waste is properly handled and recycled to minimize the environmental impact and protect public health. E-waste is a valuable resource, containing many precious metals that can be recovered and reused, providing a sustainable alternative to mining virgin materials. Recycling e-waste helps create a circular economy, where materials are reused and repurposed, reducing resource depletion and environmental impact. Developing a robust e-waste recycling infrastructure creates new jobs and stimulates economic growth, especially in urban areas. Continuous innovation in e-waste recycling technologies is leading to more efficient and sustainable processes, further improving the environmental and economic benefits. The image showcases a modern, clean, and efficient e-waste recycling facility, conveying a sense of innovation and environmental responsibility in this industry. Traditional mining involves extracting raw materials from the earth, which can have significant environmental impact like deforestation, habitat destruction, and pollution. Urban mining, on the other hand, refers to recovering valuable materials from discarded products like e-waste. This offers a more sustainable alternative to traditional mining, reducing resource depletion and environmental damage. The key difference is that urban mining focuses on recovering materials from waste streams rather than extracting new raw materials from the earth. This makes urban mining a more environmentally friendly approach that can help conserve natural resources and minimize the negative impacts associated with traditional mining practices. The circular economy is all about reducing waste and keeping materials in use for as long as possible. We need to focus on the 3 R's: reduce, reuse, and recycle to minimize the production of e-waste. Designing products for recyclability and using recycled materials creates a continuous loop of production and consumption. Manufacturers need to take responsibility for the environmental impact of their products throughout the entire life cycle, including proper e-waste management. Educating consumers on responsible e-waste disposal and encouraging sustainable purchasing choices is crucial to creating a circular economy. Small-scale recycling initiatives are community-driven efforts to collect, sort, and responsibly dispose of electronic waste. These initiatives often involve local organizations and residents coming together to host recycling drives and events with designated drop-off locations. Schools are also integrating e-waste recycling into their curriculum, educating students on the importance of responsible disposal and promoting awareness. Repair cafes provide spaces where volunteers help people repair and reuse their electronic devices, extending their lifespan and reducing waste. Artists are also finding creative ways to repurpose discarded electronics, turning them into innovative sculptures and highlighting the potential for reuse. These small-scale initiatives demonstrate the power of community engagement and collaboration in addressing the growing issue of e-waste. Robotics are revolutionizing e-waste recycling, with automated systems that can efficiently sort, dismantle, and process electronic waste, reducing the need for manual labor and improving safety. Artificial intelligence, AI, algorithms are being used to identify valuable materials in e-waste and optimize recycling processes, leading to greater efficiency and higher recovery rates. Biorecycling, using microorganisms to break down e-waste materials, offers a sustainable and environmentally friendly approach to recycling electronic components. Closed-loop manufacturing, where electronics are designed for recyclability and recycled materials are used in new products, is fostering a circular economy and reducing waste. EPR shifts responsibility for e-waste management from consumers to producers, holding manufacturers accountable for the environmental impact of their products. This can involve financial contributions, collection programs, or design requirements for recyclable products. EPR incentivizes manufacturers to design more sustainable products and reduce their environmental footprint. EPR encourages manufacturers to adopt sustainable practices throughout the product lifecycle, including using recycled materials, reducing packaging, and designing for recyclability. EPR programs promote innovation in e-waste recycling technologies, leading to more efficient and environmentally friendly processes. Governments play a crucial role in addressing the e-waste challenge through various policy interventions. One key area is promoting e-waste collection and recycling programs, such as providing incentives and infrastructure to make it easier for citizens and businesses to properly dispose of their electronic waste. Investing in modern recycling facilities is also essential, as this helps build the capacity to process e-waste in a sustainable manner. Implementing extended producer responsibility (EPR) schemes is another important policy lever, as it holds manufacturers accountable for the end of life of their products, incentivizing more sustainable product design. Strict enforcement of environmental regulations is critical to deter illegal dumping and ensure responsible e-waste management practices are followed. Overall, government leadership and a comprehensive policy approach are vital to addressing the growing e-waste challenge and transitioning to a more circular economy. Educating the public about the hazards of e-waste and the importance of proper disposal is crucial to increase recycling rates. Establishing convenient drop-off locations makes it easy for people to recycle their old electronics, which is key to a successful e-waste collection program. Offering curbside pickup services, similar to regular waste collection, can further improve accessibility and encourage more people to recycle their e-waste. Providing financial incentives, such as rewards or discounts, can motivate citizens to actively participate in e-waste recycling. Partnering with businesses, including retailers and electronics manufacturers, can help facilitate e-waste collection and ensure a comprehensive recycling system. Investing in recycling infrastructure is crucial to improve efficiency, reduce environmental impact, and build a more sustainable waste management system. Building new state-of-the-art recycling facilities with advanced sorting, dismantling, and processing technologies is essential. These facilities should be designed for maximum efficiency and minimal environmental harm. Upgrading existing recycling infrastructure is also important. Modernizing equipment, implementing automation, and improving waste management practices can boost efficiency and reduce environmental impact. Investing in training and education for workers is key to supporting these upgrades. Together, building new facilities and upgrading existing ones will create a robust, high-performing recycling infrastructure that can handle growing waste volumes and contribute to a more sustainable future. EPR schemes shift responsibility for e-waste management from consumers to producers. Producers may be required to contribute financially to e-waste recycling programs. Producers may be responsible for establishing collection programs for their products at the end of life. Producers may be required to design products for easier recyclability. Producers may be required to take back their products for recycling or disposal. Regular inspections of recycling facilities and waste management operations are crucial to ensuring compliance with environmental regulations. Strict penalties and fines for violations send a strong message and discourage illegal dumping, encouraging more responsible waste management practices. Public education and awareness campaigns play a key role in preventing violations and promoting environmentally responsible behavior among citizens. International cooperation is essential to enforce environmental regulations and combat the illegal movement of waste across borders. Businesses have a key role to play in designing electronics for recyclability. This includes using easily separable materials, minimizing hazardous substances, and incorporating recycled materials. Businesses should also plan for the end of life of their products and enable recycling. Businesses can encourage responsible consumption by offering durable, reparable, and recyclable electronics. They can provide extended warranties, repair services, and take-back programs. Transparency around sustainable materials and manufacturing processes is vital. Consumers should dispose of electronics responsibly through designated recycling programs. These programs often involve drop-off locations, curbside pickup, or partnerships with e-waste recycling companies. It's important for consumers to research and choose reputable recycling options. Both businesses and consumers should advocate for policies that promote sustainable e-waste management. This includes legislation requiring manufacturer take-back, extended producer responsibility, and investment in recycling infrastructure. Designing products with recyclability in mind is crucial for a more sustainable future. When selecting materials, choose ones that are easily recyclable and avoid hazardous substances that can contaminate the recycling process. Modular design allows for efficient disassembly, making it easier to recover and recycle individual components. Simplifying the assembly process helps facilitate easy disassembly during the recycling stage. Using standardized components ensures compatibility with existing recycling systems, improving the efficiency of material recovery. Clear labeling of materials and components helps waste sorting facilities properly identify and sort items for recycling. The core message of this slide is the 4 R's of responsible consumption: reduce, reuse, recycle, and advocate. Reduce. Emphasize the importance of only buying what you truly need, avoiding unnecessary consumption. Reuse. Highlight the value of repairing or refurbishing items instead of discarding them, extending their useful life. Recycle. Stress the need to properly dispose of items, ensuring they are recycled or disposed of responsibly. Advocate. Encourage the audience to support sustainable practices and policies that promote responsible consumption. These 4 principles work together to help reduce waste and environmental impact through our daily consumption choices. E-waste, or electronic waste, is a growing environmental concern as more and more people upgrade their electronics. Participating in e-waste recycling programs is an important way for individuals to responsibly dispose of their old electronics. There are several convenient options for recycling e-waste, including drop-off locations, curbside pickup, manufacturer take-back programs, and mobile recycling events. Drop-off locations can be found at recycling centers, electronics retailers, and city halls, making it easy for residents to recycle their unwanted devices. Some municipalities offer curbside pickup services, which provide a hassle-free way to recycle e-waste. Many electronics manufacturers have take-back programs that allow consumers to return old devices for proper recycling. Mobile recycling programs bring recycling bins to various locations, making it more accessible for people who don't have access to fixed collection points. By participating in these e-waste recycling programs, we can all do our part to reduce the environmental impact of electronic waste. The issue of e-waste is a growing global problem that requires our attention and action. As concerned citizens, we have an important role to play in advocating for sustainable e-waste management. One key step is to raise awareness about the risks of improper e-waste disposal, which can harm the environment and human health. We can also support local e-waste recycling programs by participating in and advocating for these initiatives in our communities. Contacting our elected officials is another way to push for stronger regulations and policies around e-waste management. Advocating for extended producer responsibility, EPR, schemes is crucial, as this holds manufacturers accountable for the end-of-life management of their products. Finally, we can support businesses that are committed to responsible e-waste practices, using our purchasing power to drive change. The future of recycling is here, with advancements in technology transforming the way we process electronic waste. This image depicts a futuristic e-waste recycling facility, where robots and AI systems work together to efficiently and cleanly process electronic devices. The bright, innovative environment showcases the progress being made in this field, as we strive to find sustainable solutions for managing our growing electronic waste. These cutting-edge technologies are enabling us to recover valuable materials and reduce the environmental impact of e-waste, paving the way for a more circular economy. As we continue to innovate, we can look forward to even more advancements that will help us build a cleaner, more sustainable future. Recycling technologies are advancing rapidly, with innovations in robotics, AI, biorecycling, and closed-loop manufacturing. Robots are automating sorting, dismantling, and processing of recycled materials, improving efficiency. AI is optimizing recycling processes to maximize recovery and minimize waste. Microorganisms are being used to break down e-waste in a sustainable way through biorecycling. Closed-loop manufacturing involves designing products for recyclability and using recycled materials, creating a circular economy. These innovations are transforming the recycling industry and moving us towards a more sustainable future. The linear economy model is the traditional take, make, dispose approach that leads to resource depletion, pollution, and waste. In contrast, the circular economy is a closed-loop system focused on reducing, reusing, and recycling to promote sustainable practices, resource conservation, and minimized waste. This slide sets up the key difference between the linear and circular economy models, which will be the focus of the presentation. The visual contrasts the two models, using images to clearly illustrate the linear take, make, dispose flow versus the cyclical reduce, reuse, recycle approach of the circular economy. I'll use this slide to introduce the core concept of transitioning from a linear to a circular economy, which is critical for addressing the environmental challenges posed by our current electronic systems. Sustainability and environmental justice are critical issues, especially when it comes to e-waste management. Marginalized communities often lack access to safe and responsible e-waste recycling options. We need to ensure equitable access to these services. Environmental burdens from e-waste disproportionately impact disadvantaged groups. We must work to prevent this environmental inequity. The labor conditions and worker safety in e-waste recycling facilities are major concerns that need to be addressed. Empowering local communities to participate in developing e-waste solutions is key to creating lasting change. The image on this slide depicts a diverse group of people from different countries working together to develop solutions for e-waste management. International agreements like the Basel Convention promote environmentally sound e-waste practices globally. Countries regularly exchange best practices and technological advancements in recycling to improve e-waste management. Developing countries receive support to build their capacity and expertise in e-waste infrastructure and recycling. Collaborative research projects focus on developing innovative recycling technologies to address the growing e-waste challenge worldwide.